Okay, guys, so this is a podcast. It is not going to be that interesting. I promise you. Sorry, there's no pretty pictures, or it's me writing and me talking just like it would be in a lecture. So you have to pretend I'm here. How about that? So in your books, open up to page 658 and 659. I'll give you a chance to do that. You can turn this off. And if you'll notice, there's some different theories that are written there. Right? And the very first theory that you run into is the Arrhenius theory. Oops. And that Arrhenius theory, and you should be taking notes, all right? And there's the Brønsted-Lowry theory. And Brønsted-Lowry is actually two gentlemen's names, and actually they did give credit to two different people at the same time, which is unusual. And there's something called the Lewis model. Now, normally anything else you have the ABCs, right? When you see the ABCs, this is the ABLs of acids and bases. So acids and bases are the ABLs. What are the ABLs? Arrhenius, Brønsted-Lowry, and Lewis. And those are the models. Now, let's talk about the Arrhenius theory. You already know what the Arrhenius theory is. You're familiar with this pH scale. It goes from 0 to 14. And if I have an acid, then that acid is from 0 to 7, right before 7, and neutral is 7. An alkaline goes up to 14. So let's go back here. Now let's clear my annotations. Actually, I'm going to leave them and go to the next page. So you know that if you have a pH scale, it goes from 0 to 14. Okay? And A comes before B. Smack in the middle is neutral. And so everything from here over is an acid. And everything from 7 up is a base. 7 up, not really 7 up, but you know what I mean? So, neutral. Now, what do you know about acids? Acids have hydrogen ions. And bases have hydroxide ions. And that turns out that the theory that you know already when you walked in this class, and then the class last year in chemistry, was the Arrhenius theory. All right, we'll look at this in a second in a chart format so you can organize it. But let's go back here. And if you look, what's neutral? Well, hey, water's neutral, isn't it? And what is water? Hydrogen ions and hydroxide ions combined. How about that? And so at pH of 7, all the H equals all the OH. That's what a pH of 7 means. All the hydroxide ions, these are hydroxide ions right here, correct? Equal all the hydrogen ions, and they make something called water. They're equal to each other. Now, what are some things you know about an Arrhenius acid? They turn litmus paper red. They have a pH of 0 to almost 7, right? They're sour tasting, okay, like oranges, and, you know, they make your lips pucker up. Bases are bitter. They turn litmus paper blue, and they're slippery. So in reality, fish, if you catch a fish, is most likely covered with a base because it's slippery. It's covering that base so it protects itself from an environment that could be acidic. Now, this is from 7 up to 14. Okay? And this is something like Drano. So before I go ahead and do all these different things that are on here, let's go ahead and look at the pH scale. Here you go again, acid and alkaline. And let's look at actually what are some different things that are on here. Okay, and if you turn in your book to, oh, is there a chart in here? Yeah, there is. Page 667. It's a chart that's similar to this, except it's flipped, isn't it? They have the bases at the top and the acids at the bottom and a neutral. But you look, blood is a little bit basic, milk is a little bit acidic, but it's still towards neutral. Battery acid on this chart up here on the board is pH of 0. Lemon juice is 2. Eggs and seawater are 8. Milk of magnesia is a 10. Liquid Drano is 14. So that's what an acid and a base is, and you already know that. So that's the Arrhenius model. Okay, and actually, let's take a look at, and we'll take notes real quick here before we go on. And let's look at this. This is a really good site if you go into organic chemistry. Leah Forsyth, she's great. So she delineates what an acid and a base are. And in Arrhenius, in water, you have hydrogen ions present, and underneath that H plus should be AQ, but you know that. And under OH minus in water, it should be AQ. That's a base. That's the Arrhenius theory. That's what you know. Now, let's go ahead and just write these notes down, and we'll come back to Brønsted-Lowry in a second. We're going to do Lewis another day. Brønsted-Lowry is a hydrogen donor, a hydrogen thrower, and a Brønsted-Lowry base is a hydrogen ion catcher or hydrogen ion acceptor. So I'll let you write down the Brønsted-Lowry and the Lewis. You can pause this if you want to. Okay. And again, we're going to talk about Arrhenius and Brønsted-Lowry today only. So, if you look in your book, back to page 658 and 659, it talks about Arrhenius concept, and that's just a general terminology, and he was actually doing stuff with acids and bases and some equilibrium and stuff. And then along comes Brønsted and Lowry, a Danish chemist and an English chemist, and they talk about proton donors and proton acceptors. So let's look at what a Brønsted-Lowry is. And remember, this is just a really quick overview. So Brønsted-Lowry says, you know what? I have some other stuff going on. For instance, if I have, they like to say H, well, you know what? I'm sorry. Let's flip to a better example. Let's flip, your book's not a good example here. Flip to the back of this chapter with me, please, as you hear me turn my pages. To page, sorry, this is Friday night at 8:30. So doing this for you, so you guys are good next week. So let's look at the equations on page 712. Turn. Number 29. Pause this. Okay, now, it says in these following reactions, identify the acid, the base, the conjugate base, and the conjugate acid. So let's just go ahead and do this through an example. So I'm going to go ahead and copy down HF. Okay, plus H2O, double arrow, F minus ion, and the hydronium ion. Okay, and this is a liquid, this is aqueous, this is aqueous, and this is aqueous. We don't need to worry about that right now. As a matter of fact, I'm not going to. But let's look and see what happened. I need to tell you what the conjugate acid, the conjugate base, and the acid and the base are. Well, normally what would you say an acid is? In the Arrhenius model, an acid is a hydrogen ion, right? Something like HCl or HBr. And I'm going to go ahead and let go of the blues guys. So here we go. This hydronium ion is a base, like NaOH, right? Or KOH. And what do we know about Arrhenius acids before we do Brønsted-Lowry? We knew that they're the clobber snipers, right? What are the clobber snipers? They're the strong acids. So what are the clobber snipers? And actually, I probably should write that small, so you recognize that it's different. That's what? HCl, HBr, H2SO4, HNO3, HI, and HClO4. Those are all super strong acids. I put them in water and they're going to completely dissociate. Completely. Their strong bases were group 1 and group 2. So it's things like NaOH, potassium hydroxide, okay? And this is group 2, calcium down. Now remember, you're just taking notes today, okay? Kind of give you an overview. I'm going to give you a couple problems to do, but this is really just to get some information in your head. So that's an Arrhenius acid, an Arrhenius base. Okay? So if you look at Brønsted-Lowry, they found that one of these was an acid and one of these was a base. Okay? Well, that's weird because I see something with hydrogen in it, don't you? I know it's not a strong acid because it's not a clobber sniper, but I know it's an acid. Why do I know it's an acid? Because it begins with H, according to the Arrhenius definition. But do you see OH in water? It's just water, isn't it? So what turns out, and this is a fairly good example, but what turns out is you need to figure out who's throwing and catching. So in Brønsted-Lowry, you have an acid and a base, and you have a conjugate acid and a conjugate base. Well, let's see which ones each of these are. Sometimes you need to be a detective and say, what happened on this side? Well, to figure out what happened at the beginning, I need to look at both of these. So what happened? What do you have to do to this side of the equation to make it go back to what it looked like before? Who threw and who caught? Well, ask yourself, on this side, my reactant side, what had to happen here? Didn't an H plus have to get tossed here? Because if an H plus gets tossed, then all you're left with is fluorine, right? If this H goes away and attaches itself to this water. And then what do you have? H3O plus. So I have H, and I have F. H2O makes fluorine plus H3O plus. What happened? This hydrogen went flying through the air and is attracted to this water. Leave me just with fluorine. And now what do I have? My hydronium ion. So this is my acid and this is my base, because according to the Brønsted-Lowry theory, the hydrogen donor or the hydrogen thrower is throwing to the hydrogen acceptor or the hydrogen catcher. They're playing throw and catch with the hydrogen ion. Now, what happens on this equation is that there's an equilibrium, isn't there? So let's come up here and look. What has to happen on this side between the fluorine and the hydronium? That's called a hydronium ion, water with an extra hydrogen, plus positive ion now, hydronium. What has to happen to these two to make it go back to look like this? Well, doesn't this toss back here? Right? If I do that, don't I add the H back to the fluorine? So it looks like this again? This is what it looks like on this side, right? Now it doesn't look like this again. Okay, so what do we call this right now? What's being tossed? The hydrogen. So this is the thrower now, isn't it? So this is my acid. Why? Because it's throwing. And this is my base. Why? Because it's catching, isn't it? Like this now? Right? Isn't this happening? Hydrogen thrower and hydrogen thrower. Except this is the acid to begin with, and this is the base to begin with. So we're going to call this, on this side, the conjugate acid. Conjugate acid. And this is going to be the conjugate base. It's what happens after this throw and catch occurs. So acids and bases are on this side, not based on whether they're hydrogen and hydroxide ions. That's the Arrhenius, right? Didn't Leah Forsyth tell us that the hydrogen and OH are the Arrhenius? Now we're talking about donor and acceptor. So let's do another problem. Let's do the problem on same problem 29b. H2SO4 plus H2O, double arrow, H3O plus HSO4 minus. Okay, forget states of matter and all that stuff for right now. What happens? Label the acid and the base according to the Brønsted-Lowry. Because I don't see any OH ions here, do you? I don't. So something else is going on, just not H and OH. It's more complicated. It's called the Brønsted-Lowry. So what do you have here? Is this happening? I think it is. I think that one of these hydrogens is getting tossed in the air to this water. And how do you know that? Because on this side, what has to happen on this side to make it look like my reactant side? Doesn't my H3O plus have to throw a hydrogen to this HSO4 minus? And if this HSO4 minus gains another hydrogen, it goes back to being H2SO4. So who's throwing? This is donating or throwing. And this is an acceptor. So what do we call a hydrogen donor and a hydrogen acceptor? This is an acid, and this is a base. What about on this side? Well, this is a donor, and this is an acceptor. except that's not what we started out with. This is what happened after this throw and catch took place, right? This is throw, and this is catch. So after the initial throw and catch takes place, what happens on the product side to make it go back? These are called the conjugate. The conjugate what? Well, if this is a hydrogen donor, it's a conjugate acid. And this is the hydrogen acceptor, it's the conjugate base. Okay? All right. You try C, and then you're going to go ahead and pause this, and then turn it on, and try it. All right, now, I've got this reaction. And again, sorry I didn't have this written up before, but what's happening? Who's throwing and who's catching? I think this is throwing because this H disappears on this side, right? I just have SO4. So this is my acid because it's my hydrogen donor. And this is my base because it's my hydrogen ion acceptor. Right? Now what happens on this side? The toss occurs in the other direction. Write this H plus with an arrow to help you. So this is throwing, right? It donates a hydrogen. And this catches a hydrogen. Right? Throw and catch. Fancy word for catch is accept. So that's an acceptor. So this is my acid, but what kind of acid? A conjugate acid. And this is my conjugate base. Now, when I turn this podcast off, you're going to go ahead and do number 30, and you're going to turn it in. Okay? All right. Let's look at 32. It says to classify each of the following as a strong acid or a weak acid in an aqueous solution. Well, what are your strong acids? Your clobber snipers. What were those again? Repeat after me. HCl, HBr, H2SO4, HNO3, HI, and HClO4. Now what's true if these are strong acids? What theory do these fall under? Do these fall under Brønsted-Lowry or Arrhenius as acids? Well, if you look, they all have hydrogen ions, don't they? And by being a strong acid, that means if I put HCl in water, and I have it in a bottle that says aqueous, a strong acid completely dissociates. That means it splits completely into hydrogen, into chloride ions. So even though I have a bottle that says HCl aqueous, in that bottle I have no HCl floating around like a blob. It's split completely apart into hydrogen and chlorine. So what's that mean? That means when I put HCl, a solid, into water, water comes along and says, you know what? I don't want you to stay together. I'm going to split you apart. So there's none of this here at all. Even though the bottle says that, there's only hydrogen and chloride ions. Your job in 32 is just to classify them if they're strong or weak. So if I said HF, is HF an acid or a base? It's an acid. According to what theory? The Arrhenius theory. Why? Because in the Arrhenius theory, what happens? You're talking about hydrogen ions in water and OH ions in water, right? Correct? So is it a strong acid? Nope. How come? Because it's not a clobber sniper. It's not one of these. So this is a weak acid. And what's a weak acid mean? Well, a weak acid means that when you put it in water and you dissociate it, you have HF, aqueous. It does not completely split apart. So it has an equilibrium arrow, and it's got H plus and F minus, aqueous, aqueous. So when I see a bottle of HF, I know it's not a clobber sniper. I know it's an Arrhenius acid because it begins with an H. And if you look at what happens right here, this double arrow means that I have mostly hydrogen fluoride dissolved as a blob and very little H plus and very little F minus. That makes it a weak acid because I have very little of this. Why is hydrogen chloride or hydrochloric acid a strong acid? Because I have all the hydrogen ions that used to be in this. They're now dissociated. And what makes me a Arrhenius acid? Lots and lots and lots of hydrogen. Okay? All right, so that is a brief overview of Arrhenius and Brønsted-Lowry. So let's go ahead and figure out how to do the pH. I can actually find the pH. Do me a favor, though, and flip to page 688, and let's just look at some vocabulary. Okay, on 688, there's some acids called polyprotic. And polyprotic acids can furnish more than one ion. So this is a polyprotic acid. This is not. This is a polyprotic acid. Okay? Excuse me. This is not. This right here has, well, that's a bad example. Let's look at this right here. How many hydrogens does this have? This has 2, doesn't it? Which means when it splits apart, it splits into this and gets rid of a hydrogen ion, and that's a negative. And what can happen? Can't this dissociate again and form, if I was to associate this, what would happen? This could also donate a hydrogen ion, couldn't it? Do you see that? Because there's 2 of these, it can dissociate 2 times. What about this H3PO4? It can split apart and form a hydrogen ion. And this polyatomic ion, you're just watching right now, you don't have to need to write notes, you can just look in the book. This can split apart again, can't it? This H2PO4 minus. And then another hydrogen to get rid of. And this forms HPO4. This is actually -1. Sorry, I'm tired. This is -1. This is -2. And this can split apart to just form this. You follow how that works? You see? So these are called polyprotic because they have dissociate in a stepwise manner, 1 proton at a time. This is a fancy name. It's called triprotic because it's got 3. Okay? So that's what a polyprotic acid means when you look at that. Right now, let's talk about how to find pH. Okay? And that's why it's really important that you know the strong acids and the strong bases. Turn back with me to page 670. Okay? Now, 670. How do I find the pH of strong acids? Well, it's very important you know what the clobber snipers are. What are they? Clobber sniper. HCl, HBr, H2SO4 is the last I'm going to write them out like this. HNO3, HI, and HClO4. Those are the strong acids. So, to find the pH of a strong acid, if you look at A and B on page 670, it says very clearly that I'm finding the pH of 0.1 molar HNO3. And yeah, it says it's a strong acid, but you got to look at that right now and tell me, is it a strong acid? Yes, it is. Why? Because it's a clobber sniper. So what's that mean that happens in water, folks? That means it completely dissociates and forms this, doesn't it? Okay. Now you are taking notes, if you haven't been. I told you to stop on the other page. It completely dissociates. What's that mean? That means you have none of this left, correct? Okay, now, pH. Whenever you see a P in front of something, that means negative log. So, oh yeah, you need your calculators out. Okay, a negative log of what? Well, of my hydrogen ion. Okay? Now, what did we know? What are they telling us? They're telling us that I have a 0.1 molar solution of HNO3, which means that I'm going to take the negative log of my hydrogen ion concentration, which in this case is 0.1 molar. So when you press that on your calculator, you should get a pH of 1. Is that true? Okay. And we'll talk about, excuse me, it's a negative, right? Negative log, so You press log of 0.1 molar, or you can do negative log. You put it in your calculator, and you should come up with 1. Now if you notice, there's no units. And we'll talk about where we take out these places, because pH is weird with significant figures. But for right now, let's just go ahead and write that down. Okay? Now, how do I find out the pH? Let's go back here to page 665. Okay? How do I find the hydrogen and hydroxide ion concentration? Okay, we'll do pH and pOH in a second. How do I find the hydroxide and hydrogen ion concentration? Well, there's an equation called Kw. That's a capital K. What's that mean? Equilibrium. Okay? And it turns out we're talking about water for this. So we're talking about the equilibrium in water. And what is the equilibrium in water? Well, if you have water, it can form hydrogen and hydroxide, hydroxide and the hydronium ion. Okay? Whenever you see H3O+, that also really means that you have H+, because it's a water and a hydrogen ion. So that's what this is equal to. So what's in water? We're going to say that OH- is in water, and that hydrogen is in water. Right, the hydrogen ion. Okay, so hydrogen ion, the hydroxide ion. That's the same thing as saying okay, you got to really clearly recognize this, that the hydronium ion is the same thing as saying the hydrogen ion right here. So these mean the same thing. Okay? All right, I'm going to erase this, because typically, and I don't know if you remember this from last year or not, or if you learn this, that is an equation. So what happens, this is really handy because the Kw for water is always 1.0 times 10 to the negative 14th. Now what's cool about that, and a way to remember that, is what's true? What's the pH scale? The pH scale equals 14, doesn't it? Okay? And that means that on my pH scale, if I was to draw it like this and draw a box, and make it pH of 0 and pH of 14, and draw a line like this from corner to corner, and this is pH of 7 in the middle. These are all the hydrogen ions, and these are all the hydroxide ions. So what do you notice at pH of 0? I have no hydroxide ions and all hydrogen ions. What happens as I go along, and this isn't the best picture, but you get the idea, as I go along this scale, I have less and less hydrogen and more hydroxide until I reach a point where I have all hydroxide ions. So pH of 14 is all OH minus, and pH of 0 is all H plus. What's the total scale? 14. So in sample exercise 14.3 on page 665, A says you have a concentration of 1.0 times 10 to the negative 5th molarity of hydroxide. Find the hydrogen ion concentration. Well, you know this is true. You know that the H and the OH multiplied together give you 1 times 10 to the negative 14th. No units, right? No units because it's a K, an equilibrium constant. This has units. They give it to you in A on page 665. You plug in and you find the value by solving for H plus. How do you do that? You divide both sides by 1.0 times 10 to the negative 5th, and you end up with a hydrogen ion concentration of 1.0 times 10 to the minus 9th. Okay? Now, whenever there's a 1 here, you can always find the pH. What's the pH? The pH equals the negative log of my hydrogen ion concentration. Okay? So I'm going to tell you right now that that's the pH. You put it in your calculator and you see what you get first. Okay, I'm not going to tell you what the pH is. You see if you can figure it out. But if there's a 1 there, you're going to find that this, forget the negative exponent that's taken care of here, is going to be equal to the pH. Because this is 0.0000 1, 2, 3, 4, 5, 6, 7, 8, and a 1 right there. So that's a pH of 9, isn't it? Okay. Now, what do I know about this? Let's go ahead and do B. Okay. Sorry, the custodian's coming in and out, and I'm trying to get out of here so I can finish your test. And here we go. So in B, what do I have? I have a hydroxide concentration of 1.0 times 10 to the minus 7th. I'll come back to what I was going to say in a second. Okay, let's just try another one here first, and then I'll come back to what I was going to tell you. So if you look at that, what do? I've got a Kw equals hydrogen ion concentration times hydroxide ion concentration, and that is equal to 1.0 times 10 to the negative 14th, because that's the whole pH scale. In B, they give me that the OH concentration is 1.0 times 10 to the minus 7th. This is equal to 1.0 times 10 to the minus 14th, and this is X. Right, my hydrogen ion concentration. What is my hydrogen ion concentration? What's my molarity? Well, you solve for X, and when you solve for X, you get 1.0 times 10 to the minus 7th. Okay? Now, what's true here? Do you see how the OH minus concentration is equal to the H plus concentration, aren't they? 1.0 times 10 to the minus 7th, 1.0 times 10 to the minus 7th. What do I say about H and OH when they're equal to each other on that pH scale? They're the pH of 7, aren't they? And if you notice, what's the pH here? Well, what's pH? Negative log of my hydrogen ion concentration. You can put it in your calculator if you want to. But bottom line, I can look at this. This is a 1. I can say there's a negative there. I'm going to take that exponent, and that's a pH of 7. Okay? And again, we'll worry about 7.0 or whatever, how we write that later. But it's a pH of 7, which is neutral, because this is true. They're equal to each other. Now let's go back here, and let's look at this. What was true here? This is 10 to the minus 9th, and this is 10 times 10 to the minus 5th. And how do you determine pH? pH is based on the pH scale, and if it's closer to 0, it's an acid, to 7. If it's above 7 to 14, it's a base. So what's our pH? Our pH is 9. Why do we know that without plugging it in? There's a 1 there, and there's a 9 here. That minus gets taken care of in this log. If you don't believe me, plug it in a negative log of hydrogen ion concentration, plug that in, you will get 9. Okay, 9 point whatever, again, we'll worry about that later. And if you have a pH that's greater than 7, then you have a base. If you have a pH that's equal to 7, then you have neutral. Okay? So that's how you do those. And I'm going to go ahead and flip in a second after I show you one more problem. And I want you to go ahead and do another problem. Okay, do problem or two in the back of the book, back of the chapter. All right? But let's go ahead and try sample exercise 14.5 on page 667. So turn to 667. Okay, now I want you to find the pH and also find the POH. I'm going to go through these two examples with you, and then you're going to try a couple by yourself. So, find the pH and the POH for the following solutions. For A, they give me a hydroxide ion concentration, 1.0 times 10 to the negative 3rd molarity of hydroxide ion concentration. So what do I know? I know that Kw equals OH minus NH plus. And there's no right or wrong way to do this. I know that pH, there's all kinds of ways, equals the log of my hydrogen ion concentration, negative log. POH, because P means negative log. POH means negative log of my hydroxide ion concentration. Okay, and they want me to find the pH and the POH. And I'm going to tell you also that I want to find the hydroxide ion concentration and the hydrogen ion concentration. Well, we already know the hydroxide ion concentration, don't we? That's this right here. So how would you find the hydrogen ion concentration? Couldn't you take this value and plug it in here? Right? And what do you know Kw is? You know that Kw is equal to 1.0 times 10 to the minus 14th. don't you? And that's equal to 1.0, because that's the hydroxide ion concentration, times 10 to the minus third, times hydrogen ion. And if I solve for x, I'm going to go ahead and get 1.0 times 10 to the minus 11th. That equals my hydrogen ion concentration, and that's molarity. So I'm going to write that over here, 1.0 times 10 to the minus 11th, molarity. This is 1.0 times 10 to the minus third, just by plugging that in the equation, right? Now what's the pH? Well, what did I tell you about 1s in front? If there's a 1 in front, is there? Yes, there is, and this is the hydrogen ion concentration. And I can find the pH from it because I can plug it into my negative log of my hydrogen ion concentration. So on my calculator, I could do this. And you can try it. But I'll tell you right now that that's going to equal 11. Okay? Now, I'm going to tell you to repeat after me. pH is weird. Say it. pH is weird. Okay, now we're going to talk about significant figures. How many significant figures do you see here? 2. So that means I have to write 2 significant figures here. That means my significant figures in pH are after the decimal point. We'll talk about why. There's abscisses, mantisses, have to do with this times the power, and there are all these different ways. It's in the index in your book if you really love math. But because of the abscisses and the mantisses, when you have exponents times the power of negative third, etc., or negative 11th, you need to, whatever the significant figures are here, too, you have those 2 significant figures after. I'm not going to worry about that so much. I just want to plant that in your brain. Okay? Now that's the pH. What can you tell me right now about this pH? I'm going to tell you it's a base. Why? Because it's greater than 7. Okay? Therefore, it's a base. Right? pH greater than 7. Now, how can you find pOH? Well, there's a couple of different ways. You can remember this formula from last year. pH and pOH equals 14. So I know this is 11. And I know this is 14. I can solve for x, which gives me what? 3. Okay. Now there's not a pOH scale, there's a pH scale, right? pH balanced shampoo, etc. I write 2 significant figures here because there's 2 significant figures here. And again, I don't care right now. As long as you get the 11 and 3 and follow what I'm doing, you're cool. Now there's a couple of different ways I can do this also. How else can I find pH? Or excuse me, pOH? I could use that equation right there. Or couldn't I take my hydroxide ion concentration if I wanted to? Couldn't I take this and put it in here? And do the negative log of my 1.0 times 10 to the minus third? And that's going to give me my pOH. Isn't that what happens? Now, let's look at this again. What's here? There's a 1. So I can go ahead and tell you that it's 3. See that right there? All right. Let's figure out if I have, for B, 1 molarity of hydrogen ion concentration. So I've got a 1 molar hydrogen ion concentration. And I want to find pH, pOH, OH minus, and hydrogen ion concentration. What are those? Well, again, I have my equations. What are they? You should be able to say them right now. Kw equals hydrogen ion concentration times hydroxide ion concentration. I know that pH is equal to negative log of my hydrogen ion concentration. And pOH is equal to my negative log of my hydroxide ion concentration. I also know that pH plus pOH is equal to 14. So at this point, you should be able to follow along what's in your book. But what they do is they plug this in here. Kw is equal to 1.0 times 10 to the minus 14th. And by doing that, they solve, and they put a 1 in there, and they find out, okay, and this is 1 molar, isn't it? They found out that your hydroxide ion concentration is 1.0 times 10 to the minus 11th molarity. Okay, oh, excuse me, minus 14th molarity. Sorry about that. Okay. And they can tell you right now that if you take the negative log of your hydrogen ion concentration, if you put this in here, negative log of 1.0 molar, you get a pH of 0. What's a pH of 0? Well, I'll tell you right now, that's a big acid, man. That's a super acid. It's below 7, it's right at 0. So what can you tell me your pH is right away? pOH, rather? It's 14, isn't it? 14.0. Why is that? And by the way, this should be 0.00 because two significant figures, two sig figs after. So why, if I have a pH of 0, do I have a pOH of 14? Because 0 plus 14 equals 14, right? Get that? Okay, one more example. Page 668, let's do the sample exercise. I know the pH of human blood is 7.41. That's the pH. Let's find the pOH, the H plus, and the OH minus concentration. Okay, so how do we do this? Well, we know that pH plus pOH is equal to 14. So if my pH is 7.41, which is really just slightly a base, isn't it? Why is it slightly a base? Because it's over 7. So my pH is 7.41 plus X equals 14. What's my pOH? I subtract, and my pOH is 6.59. Right? Now, what do we know? We know that pH is equal to my negative log of my my hydrogen ion concentration, and my pOH is equal to my negative log of my hydroxide ion concentration, correct? Now, what do I know? To get this, I know my pH, don't I? I know this, and I know my pOH. So I'm going to go ahead and write down that this is equal to 7.41. And this is equal to 6.59. So in other words, I know my pH, and I know my pOH. I need to find this. Don't I? So you do antilog. Okay, so press second log of your negative pH. So on the very bottom of your paper it says to find the hydrogen ion concentration. On your calculator you're going to press second log of your negative 7.41. Okay? Or actually it will look like this on your calculator. Negative 7.41. And to get OH minus, you press second log of your negative 6.59. Because you're doing the opposite of this now. You're anti-logging it. So when you do that, for hydrogen ion concentration, when you press second log of my negative 7.41, I get 3.9 times 10 to the minus 8th. And I'm going to label that molarity because that's what I found. For OH minus, I'm going to get 2.6 times 10 to the minus 7th molarity because I found the hydroxide ion concentration. Okay? So right now in the back of your chapter, and next class as well, okay, whatever you can get done, I would like you to try to do on page 712, we already were going to do number 30, weren't we, and number 32. I'd like you to do 37, A and B, and 38, A and B. Okay? So, again, sorry that this wasn't a beautiful podcast, that it didn't have any nice charts and everything, but you get the idea.